Welcome back, everybody. Today we'll be starting on a new chapter, Chapter 5, where we'll be discussing quasi-geostrophic theory and try to explain the large-scale weather behavior of the mid-latitudes in terms of two primary weather features, namely large-scale planetary waves and extratropical cyclones. Both of these are going to be explained in fairly thorough detail using complicated mathematical expressions following the QG theory. So as part one, we'll give an overview of exactly what we're trying to tackle here. And this is basically captured in the Norwegian cyclone model, a cyclone model that was proposed approximately 100 years ago in order to explain the development of these extratropical features. So extratropical cyclones are basically large-scale, low-pressure events. And they're associated with positive vorticity, hence the spinning nature associated with them, and they're typically large-scale features with diameter on the scale of approximately 10,000 kilometers. They're closely related to weather fronts, and so we're going to have to look at weather fronts in order to understand exactly how these features are behaving. These systems are particularly prominent in the wintertime when we have large eddy activity transporting energy from the subtropics to the polar regions. And they're responsible for basically large-scale storm systems, in particular large-scale winter storms. These are particularly prominent in the US Northeast and in Northern Europe, where these storms have the potential to cause millions to billions of dollars of damage, depending on their severity. So, in summary, extratropical cyclones are basically low-pressure systems. The eye of the extratropical cyclone is a low pressure, analogous to tropical cyclones. The primary difference is that the center of an extratropical cyclone is a cold core phenomenon, whereas tropical cyclones are so-called warm core phenomenon, where latent heating in the interior of the storm is sufficiently strong in order to bring the temperature of the core up to a high enough level in order to provide energy for the storm itself. Extratropical cyclones form through the spin-up of low-level positive vorticity, and we'll explain exactly how they go about doing that. They're closely related to divergence and convergence. Recall from previously that divergence and convergence drive vertical motion, and extratropical cyclones have large vertical motion in their interior, which are responsible for driving a lot of the vorticity associated with these storms. They're closely associated with frontal activity, namely cold and warm fronts and occluded fronts, as we'll see, and they sometimes develop rapidly and sometimes not at all, very much dependent on local weather conditions. So in order to get a better grasp on how exactly these phenomena behave, we're going to explore these in detail. So first of all, starting from the basics, we have a concept known as warm fronts. Generally, shock waves or very sudden discontinuities in the atmosphere do not exist. However, the closest thing that we do have are fronts, which are somewhat more diffuse than a shock wave, but nonetheless exhibit fairly sharp increases in temperature and other quantitative variables over a very short distance. What warm fronts in particular are typically very broadly shaped. They have this typical wedge shape associated with them and separate basically warm air from cold air. They're generally due to moving warm air, which pushes over top of a cold air region. Due to buoyancy, the warm air will then sit above the cold air and will tend to form a very slight updraft as it pushes over the cool air region. This leads to basically the formation of nimbostratus clouds, altostratus, and cirrostratus as the air is pushed higher and higher above the cold air event. The precipitation associated with warm fronts is typically minor as compared to cold front events. These fronts also typically move much more slowly than cold fronts because, as you can imagine, the wedge-type shape gives it very little lateral momentum or lateral force on the cold air, which is also typically heavier and hence more difficult to move. And these fronts typically have precipitation spread out over a larger distance. Cold fronts, on the other hand, have a very distinctly different character associated with them. Here we have a very sudden difference in terms of surface temperature as the cold front presses through the system. And these systems, unlike the wedge shape of warm front systems, kind of take a bulldozer type shape. That is, they have a very sharp leading edge, leading to very rapid updrafts at the leading edge of the front, and hence the formation formation of so-called deep convection or cumulonimbus clouds at the front itself. So this leads to typically heavy precipitation in the vicinity of the front. These fronts also typically move faster because of their shape. They are basically bulldozers. They're able to push over the warm air much more easily, and the warm air also has reduced inertia associated with it because it's warmer, lighter air. So fronts and precipitation kind of play into each other in the presence of the Norwegian cyclone model. Basically, the Norwegian cyclone model is formulated based on the conceptualization of what would happen if you had fronts interacting with one another. So in this formulation, basically you have a curved warm front, which is associated with basically cyclonic vorticity. So you have warm air which is being pushed northwards to the east of the low pressure event, and cold air which is being pushed southwards to the west of the low pressure event. So this satisfies the eddy properties that we need in order to instill mixing in the atmosphere and lead to northward transport of energy. The clouds and precipitation will typically form over a much broader distance in front of the warm front, as shown in this diagram, although the most severe storms will be found in the vicinity of the cold front. Continued rotation will lead to a cold front which pushes into the region of warm air and continues much more rapidly around the cyclone than the warm front. This also leads to the formation of different types of clouds associated with these extratropical cyclone events. Again, in the vicinity of cold air, you have cumulus clouds, whereas in the vicinity of the warm front, you typically have stratus clouds. The pocket in between is typically full of warm air, whereas surrounding pockets are full of cold air. So this can be very easily seen on weather maps here showing geopotential height contours. Here we're seeing a low pressure event at the surface, as well as a developing wave in the geopotential field. So this represents upper level geopotential. So it shows that you have basically southward propagating cold air to the left of the low pressure and northward propagating warm air to the right of the depression. Overall, the features of the geopotential are basically wave-like, so we see a development of a wave centered around this low pressure event. So, starting from the very beginning then, the Norwegian cyclone model posits that a cyclone event will be initiated when you have a boundary or front which basically separates warm air in the south from cold air in the north. This front is typically stationary, although shear is typically present, where in the warm air vicinity you typically have eastward geostrophic wind, and in the cold air vicinity of westward propagating geostrophic wind. The presence of baroclinicity is incredibly important in driving this event. When we have a low pressure event when we have a warming, for instance, that shows up above the stationary front, as we saw earlier, this leads to the formation of a surface low. The surface low then leads to generation of vorticity and leads to the generation of upward wind velocities. With the generation of vorticity, you then get that there is cyclonic activity about the low, and hence the system begins rotating. So this is the initiation of instability in the flow. Precipitation will begin to develop basically with heaviest currents along the front, where you have basically warm air moving up above the cold air and cold air pushing down into the warm air vicinity, both leading to the formation of precipitation as warm air is pushed upwards due to buoyancy. With continued development of wave intensification, you have that the cold front moves much faster than the corresponding warm front. The warm front propagates slowly northwards, whereas the cold front basically pushes south very rapidly into the region of warm air. This leads to a kink in the flow, and hence you get basically a discontinuity in the location of these fronts. This will continue to intensify and develop going forward. As the cold moves farther south, the curvature will eventually cause the cold front to overtake the warm front, and this will lead to the formation of what is known as an occluded front. That is a front which basically separates cold air from cooler air which originally underlied the warm air, and hence leads to a very rapid intensification of precipitation as the last remaining warm air that is present between those two fronts is immediately pushed upwards into the upper atmosphere, hence undergoes condensation and leads to precipitation. However, as the development occurs, this also leads to basically separation of the low pressure event. As you can see in the overhead view in this figure, the low pressure event is no longer being fueled by wind velocities from the warm, moist air in the south, and hence has become isolated. This leads to a loss of energetics for the low front, and hence will eventually lead to dissipation of the extratropical cyclone. The presence of the occluded front is depicted here. Basically, as you have cold air pushing into cool air, as shown in the top figure, you have warm air which is immediately pushed upwards and hence leading to very intense precipitation in the vicinity where these two fronts interact with one another. This is what is known as a cold occlusion and occurs when cold air pushes into a region of cooler air. A warm occlusion can also occur where you have cooler air which pushes into a cold air front. You basically get the same upward tendency associated with the warm air, and hence precipitation associated with the occlusion. But in this case, the arrangement of the cool air and cold air are switched. So in the final stage of the Norwegian cyclone model, then, we get complete separation of the low pressure event, and hence the loss of warm, moist air, which provided its initial energetics. This will then eventually lead to the low pressure system to gradually dissipate over time, and hence the cyclone will dissipate, leading to another atmospheric setup where at some later time we can potentially develop a second extratropical cyclone. However, this has fulfilled the necessary role of the extratropical cyclone in transporting energy from the southern regions where you have warmer air into the northern regions, and hence leads to rebalancing of energy across the Earth's surface.